Okay, so I'm going to walk through how you actually would do this FOILing. So by FOILing, I mean we're going to basically multiply the first part here, this y, times this y, so that's the f in FOIL, the first, and we're going to end up with y transpose y. And then we're going to multiply this part here, this outer part here, this x minus x beta hat. I'm going to multiply that by y here. So that's going to end up with, because when we distribute this transpose, it ends up flipping based on our matrix fact, the order of the multiplication. And so when we transpose x beta hat, it ends up being beta hat transpose x transpose. So if we multiply that by y, we end up with negative beta hat transpose x transpose times y. So that's the inner part. And then we've got negative y times x transpose times x beta, so that's going to be the outer. We've got this y here, this y transpose, if we pull this transpose over. And then we've got an x beta hat over here in this outer, so that's where that comes from. And then finally we have beta transpose x transpose and x beta, so that's the last there, the L from FOIL. Okay, so here's another matrix fact. The transpose of a scalar is a scalar. So what does that mean? Well, a scalar is like just a single number, so not a matrix, not a vector, just a single number, like 1 or 2 or n. These are scalars. And so if we think about the dimensions of beta transpose x transpose y, that's going to be just a 1 by 1 matrix. And we can think about that because beta transpose is going to be just 1 by, in the case of simple linear regression, it'll just be 1 by 2. Our design matrix x is going to just be x transpose. If we take the transpose of that, that's going to be 2 by n. And then our y is going to be n by 1. And so if we have a 1 by 2, 2 by n, and 1 by 1, we multiply those all together. We end up with a 1 by 1, which is just a scalar or a single number. And if we take the transpose of that, then we end up just getting the same number because the transpose means we're sort of flipping the matrix. But if you just have a number, taking the transpose doesn't actually do anything. Okay, so this is an important fact because it means that y transpose times x beta, if we take the transpose of that based on the previous fact that we knew, that equals beta transpose x transpose y. And that means that y transpose x transpose beta is going to be equal to beta transpose x transpose y because these are both scalars. So why does that matter? Well, because that means we can combine these terms on the inside. So these two terms as beta transpose x transpose y and y transpose x beta, those can be combined into one single term, 2 times beta transpose x transpose y, because each of these terms are scalars and they're the same scalar because if you take a transpose of a scalar, it's still a scalar. And so we can just multiply those by 2. So that helps us further simplify this equation. Okay, so to find beta hat that's going to minimize this residual sum of squares, what do? We already said when we want to take the minimum of something, we take the derivative and set it equal to 0. And so that's exactly what we're going to do. So let's go through some matrix facts again. So if you have A and B, which are both p by 1 vectors, and you take the derivative, if you take the derivative of A transpose times B with respect to B, or B transpose times A with respect to B, you end up getting A, this vector, as the answer. So this is important because basically what it's saying is this is kind of like when you take a derivative of a scalar. If these were just scalars, this would be like A times B. You wouldn't have to worry about the transpose. And when you take the derivative of A times B or B times A with respect to B, it's just going to be A. So this sort of, I think, tracks with what we know about derivatives. And similar when A is symmetric, if A is a symmetric matrix and you take the derivative of B transpose A times B with respect to B, then you end up getting 2 times A, B. This is the important piece that we're going to want to keep track of here. So what I want you to do is I want you to try this. So I'm going to give you a couple minutes to try it. And basically, I want you to take the derivative of this set of matrices with respect to beta. Okay, so make sure you add that derivation to your application exercise and then go ahead and knit it so that it saves. And then we'll go on to the next lesson.